Good afternoon, everyone. I'm Rong, a research scientist from the Data Infra Tetris team at Meta. Site-wide outage would cause huge costs in terms of lost revenue and damage to reputation. For example, the 6-hour massive outage in October 2021 cost at least $16 million as revenue loss. For Meta scale that span across dozens of geo-distributed data centers, seemingly rare natural disasters like hurricane blowing down the power lines occur regularly. Furthermore, man-made incidences such as network fiber cuts, software bugs, or misconfigurations can also affect the entire data centers. Today, I'm going to talk about how data warehouse handles disasters, with a focus on how we recover batch workloads at scale. Today's talk includes 3 sections. First, I'll share how their program was born at Meta and its challenges. Then, I'll give an overview of the data warehouse and our DR strategies. After that, I'll deep dive recent improvements on batch workload recovery. In October 2012, Hurricane Sandy came within 30 miles of 2 Meta data centers, Ash and FRC. The destruction of either data center would have been devastating to Meta business because Ash was a fiber optic cables hub that connect Meta to the rest of the world. FRC contains all of Meta database primaries. At that time, Meta was distributed across only 3 major data centers, and we were not prepared for the loss of an entire region. With plan to grow Meta infra at that time, the likelihood of regional disaster happening was growing. Hurricane Sandy was a wake-up call. We started to ask ourselves if we can run Meta products without one of our data centers. And the disaster program was born as a result. After Hurricane Sandy, Meta started to look at a single region failure model to understand how we can prepare our infra to handle such incidents. This map showed the current deployments of Meta regions across the world. A typical Meta region could contain multiple data centers. Any Meta region could go down due to various factors such as natural disasters or man-made incidents. The strategy for tolerating single region failure is to drain the region. We would redirect traffic away from the affected region towards other healthy regions. There are a few challenges. First, dependencies. Meta runs thousands of microservices, and dependency between all these services lead to a complex operation. And we need to join systems gracefully based on their dependencies. Second, capacity. It would be problematic if other regions already consume all the available resources when there happens, and moving more demands to other regions may cause overload. As a result, Meta decided to add extra capacity, called DR buffer, which makes healthy regions have enough resources to absorb the traffic from the affected region without adding overload risks. In addition, global replication is introduced to ensure service and data is available to serve workloads even when one of our data centers is down. Finally, failover. For stateless services, we leverage internal tuple service to handle it gracefully. For stateful services, upon failures, states like data need to be recovered and reconstructed in a timely bounded manner. Let's turn to warehouse disaster recovery. Before discussing the DR strategy, let me briefly introduce warehouse at Meta. Warehouse consists of several components that work together to provide a scalable and reliable platform for data storage and processing. Some key components. Data ingestion is the process of collecting data from various sources and loading them into a warehouse. Data sources include user activities from Meta application like Facebook website or Instagram app, and service logs from web services or internal services. Data ingestion is done using the Scribe distributed message system and FBD ETL service. Once the data has been ingested, it is stored in the warehouse using warm storage. Then, compute involves transforming and aggregating the data to create a new dataset, which is typically done using tools like Spark, Presto, and Diagraph. Both ingested and processed datasets can serve different types of workloads. Interactive workloads such as analytics, batch workloads such as hourly updated monitoring dashboards, and ML workload such as training jobs. For meta-scale, warehouse workload cannot fit into one region. Instead, workloads are partitioned by namespace, which is the logical container for data storage and compute. It provides a way to organize and manage the data in the warehouse. A namespace usually contains thousands of tables, and each table could be further partitioned into more manageable pieces called partitions. Namespaces are placed on a specific region or across multiple regions based on namespace resource requirements and available hardware in each region, with the goal to minimize costs over the planning horizon. Now let's talk about the warehouse DR strategy. For warehouse DR, there are two prerequisites: capacity and global replication. Since 2018, warehouse began to deploy extra DR buffer in each region. When disaster happens, the additional capacity enabled the health region to absorb traffic from the affected region without any overload risks. Similar to normal capacity, DR buffer includes data storage, compute, and other resources like I/O. For global replication, warehouse leveraged replication system to achieve a replication factor of 2 for each partition landed in the primary region in warehouse. Replication service make an extra copy in a different region. This is an asynchronous procedure, which means when disaster happens, recent landed data may not have backup copies available yet. As of 2023, replication operates on dozens of meta regions, and the warehouse holds tens of exabytes of data. For daily backup data, replication triggers millions of replication jobs to handle hundreds of petabytes of data copies. What could happen for warehouse users when disaster happens? For interactive workloads, users' query might fail to complete. For batch workloads, pipeline landing time could be delayed and violate SLOs due to data loss. For ML workloads, training time could be wasted due to missing data. Our mission is to minimize all these user impacts. When disaster happens, warehouse would fail over workloads from the affected region to other healthy region and recover missing data accordingly. All these operations are orchestrated via warehouse DR workflow. The prerequisites for kicking off the warehouse workflow, DR workflow, is that DR capacity is ready and the warehouse replication is healthy. The first work phase in the workflow is failover, in which we update corresponding configurations to mark the affected region to disaster status and redirect traffic to other healthy regions. This phase usually takes less than 5 minutes in practice. In reality, there could be a responsible window between the time when disaster happens and the time we recognize it. The second phase is recovery, in which we recover unreplicated backup data while replaying the original pipeline with idempotency assumption. Ingested data can be recovered via Scribe and FBETL services, and batch workload generated data can be recovered while replaying the pipelines. As is shown in this graph, the performance of batch workload replay determines how fast we can recover the missing data. And in the next section, we'll focus on recent improvements on this part. In practice, we conduct different types of DR exercises to validate warehouse DR readiness. First, we conduct tabletop exercises and DR drills with frequent cadency to highlight DR readiness risks and work with partner teams on mitigating strategies. In addition, zero-notice DR storms are meta-disaster readiness exercises where we isolate a whole production region to validate end-to-end readiness for the single region failure. Running storms help warehouse understand dependencies outside of warehouse and potential user impacts. Furthermore, we proactively run their orchestration workflow to mitigate emergencies such as capacity crunch or power loss in a certain region. As mentioned in the previous section, replicating data from the primary region to backup regions happens asynchronously. In addition, data copy could be delayed due to various reasons, such as insufficient capacity to handle burst demands, service overloading, throttling, and transient errors. Considering the warehouse data scale, when disaster happens, there could be considerable amount of recent data that don't have backup replicas yet. Now, the first question to answer: how to locate missing data? Missing data is associated with replication latency. To approximate the replication latency, warehouse use replication lag, which represents the oldest creation time of the data that have been landed yet not replicated. We've been using the replication lag SLA for warehouse DR for a long time. This matrix is easy to get and understand, and if it's under a certain hour, we have high level of confidence that when disaster happens, warehouse can fail over and recover the missing data within bounded time. The biggest issue with using replication lag as a single matrix is that it does not reflect true gap between primary and backup region, as replication system does not guarantee first in, first out semantics. It's very hard to achieve strict FIFO in large-scale distributed systems. In reality, a few replication jobs could be stuck due to various reasons, such as throttling and transient errors. In addition, load imbalance that could be caused by factors like inter-region capacity restriction further complicates the replay range. Our goal is to get exact set of missing data that landed, yet not replicated to the backup region. Given that disaster could happen in arbitrary time, it's necessary to provide a real-time view for the missing data. The solution is to build a real-time replication factor checking service that continuously monitors and updates the delta difference between the primary region and the backup region for any given namespace. After locating the missing data, the next question to answer is how to retrieve the corresponding tasks that generate this data. We need to figure out these tasks and replay them to recover the missing data in the healthy regions. The legacy approach locates all tasks with creation time falling within the window, the replication lag, and failover time. However, this approach is neither efficient nor correct. First, this approach causes quite a lot of redundancy, since it would replay data that had already replicated to the backup region, but still fall under replication lag window. In addition, there are dependencies among tasks, and failing to honor this dependency would incur failures. Here's the illustration for task dependencies. In this example, assuming we have three pipelines A, B, and C, tasks could have intra-pipeline dependencies. For example, task B2 and B3 depends on PB1, the output of task B1. In addition, tasks could have inter-pipeline dependencies. For example, task A1 depends on PB3 as input, which is output of task B3. For replay, assuming PB3 and PA1 are missing data, we need to execute task B3 first and then A1. Otherwise, task A1 would fail, and desired output PA1 cannot be recovered. The key challenge here is to construct dependencies to honor execution order, and this is the key to addressing the two biggest challenges in batch workload recovery: correctness and efficiency. The key idea is to leverage data writer to record task information when landing data. For example, when Presto finishes the computation against the input data and writes output to the warehouse, it adds the task information when registering the metadata of the output to the warehouse metadata registry. Then, to retrieve the corresponding task for the given missing data, we can extract the task information from the metadata registry. One more challenge here is the different type of data writers might record different types of task information. For example, Spark only records containing information, and we need to resort to container service to retrieve its corresponding task information. To solve the problem, we'll build a translation layer to convert various types of raw information to the standard format. For pipeline tasks, the standard format for a given task is pipeline task name and period ID, in which period ID represents the scheduled time to run the task. Most pipelines run periodically, daily or hourly, and task schedule time is needed to identify which task instances to replay. As mentioned in the previous slides, tasks could have dependencies. Building the full lineage graph to cover all dependencies is a straightforward idea, and we resorted to existing lineage tracking tooling that was built for dependency analysis. However, building full lineage graph is very expensive, and tooling couldn't provide freshness and scalability guarantees of the lineage data. What we need is real-time dependency retrieval. And the key idea to solve this challenge is to leverage the wait-for task, which is a sensor task that delays the following task until the specified data is found, and repeatedly check the data readiness. These key insights allow us to reduce the problem from building a full lineage graph to only retrieving immediate upstream wait-for tasks. Now let's go back to the previous example and see how old and new approaches work. Assuming the output data for task B2, B4, C1, and C2 are missing, and task B2's output is all this data that has been landed yet not replicated to the backup region. The legacy approach simply locates all tasks with creation time later than task B2 and replay them, which includes tasks across all pipelines except the B1 in this example. In addition, quite a few tasks would fail since they are not waiting for dependent data, such as task A1 and C1. In contrast, the new approach locates the exact set of tasks B2, B4, C1, and C2, and retrieves the immediate upstream wait-for tasks. In this example, we get two wait-for tasks, one for inter-pipeline dependency between B2 and C1, and the other for intra-pipeline dependency between C1 and C2. Then, the new approach submits the minimum set of tasks for replay, and execution order are guaranteed while the wait-for tasks. To handle the scale of missing data in Meta Warehouse, we involved the solution in multiple aspects. For freshness, to reduce the risk of unexpected delays in calculating missing data against large datasets, we built validation logic to periodically refresh missing data report cache in replication factors checking service. For completeness, we conduct extensive analysis to narrow down and categorize the unknown mapping between missing data and tasks, and build corresponding handling logics. And we further filter out unnecessary data and tasks to further minimize the false positives. For scalability, we handle missing data and tasks in batches. To enable this, we involved the solution to batch manner and build batching facilities in corresponding dependent services, such as batch task information retrieval and batch task submission. As a result, we can process large amounts of partitions and tasks in batches with partial failure support. The new recovery approach enables us to recover an accurate set of missing data in disasters, no more, no less. We have demonstrated its effectiveness against production workloads in recent DR exercises. Compared to the legacy approach that could only process tens of thousands of missing partitions, the new approach can easily process more than 1 million missing partitions during recovery. In addition, the new approach can eliminate 75% of redundant recovery and cover more than 10% missed recoveries. It does not end there. Now let's look at what lies ahead for warehouse disaster recovery. As our infrastructure grows, the likelihood of multi-region outage increases, and we anticipate to see such failure happening more often. For example, in February 2021, severe weather in Texas and Nebraska caused power disruption affecting both FTW and PNB regions. Adding capacity is a straightforward idea. However, it is not scalable when the number of region failures goes up, and we need to think about other solutions like service degradation. In addition, ML workload has a growing footprint in warehouse, and we need to build their compliance strategies for training freshness, such as reducing ML training landing delays during disasters. Lastly, I would say, none of this work would have been successful without vital contribution and support of our team members, data infra partner teams, and partners from storage and core systems. Thanks for listening to the talk. Please do get in touch with us after the talk for any questions. Thank you.